Hello everybody, welcome to another video lesson. We are starting our Trigonometric Identities unit, and we're going to start that off with some basic trig identities. We're going to be able to use our basic trig identities in order to find some trig values and simplify some expressions. So let's hop right into our concepts, which are our identities. So we've seen some of these before. These are going to be our quotient and reciprocal identities. Let's go ahead and prove this one right here that says tangent theta is equal to sine theta over cosine theta. We're going to do that with a little unit circle. So if I have a unit circle here and I have a point along my unit circle, we know that that has coordinates x, y. But we also know that because we're on a unit circle, I can think of x as cosine theta and y as sine theta. And tangent of theta, if this is my angle here, theta, right? That's going to be y over x. We know that. So if y is equal to sine theta and x is equal to cosine theta, then my tangent is equal to sine over cosine. And then the cotangent is just the reciprocal of that. So then my reciprocal identities, we've kind of seen all of these before, but just to kind of clarify that they're each are the reciprocal of each other. And let me show you what that means. So the secant is equal to 1 over cosine, right? Now, if I were to try to solve this for cosine, I would multiply each side by cosines. Those would cancel out. And I'd be left with cosine times secant is equal to 1. Now, I'm trying to solve for cosine, so I'd have to divide both sides by secant. And I'm left with cosine is equal to 1 over secant. So that maybe made sense to some people, but I just wanted you guys to see that these reciprocal identities, they go both ways, okay? I can have secant be the reciprocal of cosine, and cosine is also going to be the reciprocal of my secant. So just want us to understand those. Now let's look at 3 more types of identities here. So pause and make sure you write all these down. First one is our Pythagorean identities. This is the one that's going to be most used. However, we derive these second 2 from this first one. So I'm just going to show where this first one comes from. Again, we have a unit circle here. I've got a point here on my unit circle, and I'm going to create a right triangle with that unit circle, okay, with the point on that unit circle. Now we know with the Pythagorean theorem that a squared plus b squared is equal to c squared, right? If this is my right angle, okay, a squared plus b squared equals c squared. So my a is what here? My a is just my x coordinate, and then my b is my y coordinate, right? And then c is my radius. Now remember we said on our unit circle, again, x coordinate is just cosine and y coordinate is my sine. So I can then substitute in 1 for c squared, and then a squared would be cosine squared, and b squared would be sine squared, since those are just my x and y coordinates. Okay, so that is the Pythagorean theorem, kind of the basis for that. Now let's take a look at our cofunction identities. So our cofunction identities state that if I have the cosine of, say, pi over 2 or 90 degrees, we're going to look at 90 degrees right now, minus theta, that is equal to sine of theta. Okay, so let's prove what this means here. If I have a freestanding, freeform triangle here, right triangle, I've got an x value, y value, and an r value for my hypotenuse. My angle here, theta, is what we're looking at, which means what is this angle right here? Well, I know that all of the angles in a right triangle are going to add up to 180, right? And since this one is 90, this right angle here is 90, that means that what? These 2 angles have to add up again to 90, which means if this angle is theta, then this angle would be what? 90 minus theta, right? So 90 minus theta here. So cosine of 90 degrees minus theta, cosine would be adjacent, so that's going to be y, over r, our hypotenuse. And likewise, sine of theta, so now coming down here to sine of theta, that is going to be opposite, which again is y, over hypotenuse, which is r. So we can see that these both equal y over r, so these 2 terms, this equation checks out. Okay, so now let's look at our negative angle identities. We're going to look at this sine of negative theta is equal to negative sine theta. We're going to do this with another circle here. This isn't necessarily a unit circle, just a random circle. And I've got an angle theta that I go counterclockwise to get, starting from my standard starting position of the positive x-axis. And then I'm going to go clockwise to get negative theta. Okay, so I've got these two angles here, and I've created right triangles with the horizontal axis for each one. Now let's think, what is sine of negative theta? Well, sine of negative theta is opposite, which gives a negative y value over my hypotenuse of r. And I can think of that as negative because this whole, it's not just the numerator that's negative, right? The whole fraction is negative here. So negative y over r is what we can think of this as. Now, let's take a look at sine theta. Well, sine theta is y over r, right? If I come up here to this positive angle, y opposite over r, that's positive. However, we can see here that what we have in parentheses is equal to this y over r, right? So I'm going to substitute in this sine theta since these two are equal to each other, and I get that sine of negative theta is equal to negative sine theta. So that is the basis of where we get these identities from. I'm not going to prove every single one just for the sake of time, but that's kind of where they come from. So make sure you get all of those written down. Okay, so now let's get into our examples. First thing, we're going to find sine of theta if cosine is 1/3 and we are given a range or a domain for our angle. So we're going to start off using our Pythagorean theorem because we're looking for sine and we're given cosine. Now, some of you are probably thinking, well, I can do this without any of these identities, which is fine, but this is kind of the basis for a lot more difficult trigonometric manipulations for trigonometric equations in the future. So we really need to understand how to do this without drawing our triangle out. Okay, so we've got sine squared theta plus cosine squared theta is equal to 1. I'm going to subtract cosine squared on each side since I'm looking for finding sine. All right, so sine squared theta is equal to 1 minus cosine squared. And note that cosine squared theta is equal to cosine theta quantity squared. These two are the same thing. This is just another way of writing this. Okay, I can write these both the same way. So cosine theta we're given right here as 1/3, right? So I'm going to take 1/3 and square it, and that's going to be this term of cosine squared theta. All right, so I've got 1 minus 1/9, and that simplifies to 8/9 on the right-hand side, and I still have sine squared theta on the left-hand side. Again, sine squared theta is the same thing as what I've rewritten here of sine theta quantity squared. That's equal to 8/9. I'm going to take the square root of both sides, so my squared and my square root will cancel out. And I've got plus or minus square root of 8/9, which simplifies to square root plus or minus square root of 8/3, which again simplifies to plus or minus 2 root 2/3. Now, what are we going to do about this plus or minus here? We don't want to leave it there because we are given this information right here. We're given this boundary for our theta. Now, if I were to draw out my quadrants, hopefully you see and remember that between 270 and 300, well, that's quadrant 4. Now I have to think, is sine positive or negative in quadrant 4? Well, it's below my horizontal axis, so in quadrant 4, sine is negative. So I can go ahead and drop the plus or minus, and I'm just going to say that sine of theta is equal to negative root 2 over 2 root 2 over 3. All right, here we go. We're going to find secant, second example, if sine is negative 2/7, and we're given, again, a range for our theta. Okay, so you guys pause this video and see if you can't find secant using our trigonometric identities. Okay, here's the process, and hopefully you got that secant theta is equal to negative 7 root 5 over 15. Don't forget to simplify these fractions as much as possible and never leaving a radical in the denominator. Looking at simplifying some more expressions, we're going to simplify tangent squared theta cosecant squared theta all minus 1 all over secant squared. So we got a lot going on here. Now, if you're ever in doubt of where to start, just kind of put everything in terms of sine and cosine. That's usually a good place to start if you're not really sure, nothing's really jumping out at you. So if I put tangent squared theta and cosecant squared theta in terms of sine and cosine, we can see that we have some sines that cancel out. And now I have 1 over cosine squared minus 1. Well, I'm not going to change secant squared into anything cosine related because I know that this right here is actually secant squared, right? So let's rewrite that as secant squared theta minus 1 over secant squared theta. Now I'm going to take this fraction and I'm going to break it up into two. I'm going to expand this into two separate fractions. So I'm going to have secant squared over secant squared minus 1 over secant squared. So you can see if we can put this back together and we get this original fraction now. So my first term is just 1, and my second term is cosine squared. So I got 1 minus cosine squared at this point. Now remember our Pythagorean theorem, cosine squared plus sine squared equals 1. If I solve that for sine squared, I get 1 minus cosine squared, which is exactly what I have here. So my final simplified term is just sine squared theta. That's it. Okay, second example, simplify. You guys go ahead, pause the video again, and simplify this term right here. You are going to get it down to just one trigonometric function at the end. All right, here's the process, and hopefully you got tangent theta for that one. All right, fourth example, we are going to rewrite cotangent squared minus tangent squared theta in terms of sine. Now, this is actually a really helpful concept to understand of writing things in terms of, say, sine or cosine, especially when we get into solving trigonometric equations. So I know this seems kind of random, like, well, why do I need to put this in terms of sine? But it is going to be pretty applicable and pretty helpful for us in future math classes and in future examples in this math class and future lessons. So let's go ahead and rewrite everything in terms of sine. Okay, so I'm going to write cotangent squared. Well, that's just cosine squared over sine squared. And tangent squared I know is sine squared over cosine squared. So using our Pythagorean identity again, I know that if I solve for cosine squared, that's 1 minus sine squared, right? So anywhere I see cosine squared, I'm going to replace that with 1 minus sine squared. Okay, so it's going to look something like this. Now, technically we're done here, but I'm going to take it a few steps further and get this under one rational expression. Okay, so I'm going to combine this to be one fraction. So to do that, we need to use our LCD, or we need to find our LCD, which will be 1 minus sine squared times sine squared theta. And I would multiply each side by what we're missing in the denominator from the LCD. And now I just foiled this top part here. Foiled that, and that gives me this 1 minus 2 sine squared theta plus sine to the 4th theta. Okay, and then sine squared times sine squared on the second term gives me minus sine to the 4th theta. I got a positive sine to the 4th, a negative sine to the 4th, so those guys cancel out, and I'm left with this expression right here, all in terms of sine. So that is it, guys, for this video. Good luck with your practice.